So my name is Victor Niño. I'm the Director of Business Development for Bioequinox. And today we're gonna talk everything related to how to create a healthy and comfortable and energy efficient classrooms. So we'll discuss all the three components for how to make a very high performing classroom. So regarding Bioequinox, the mission is to develop solutions for healthy, comfortable, sustainable lifestyles, learning to live in our daily allowance of solar energy. The products we do smart, healthy, indoor air quality and comfort management systems. Our products are made in the United States, and we are very well known by the SERV2, that's a residential indoor air quality management system. And then today we're gonna discuss the SERV1000 is one of the new products that we just released. We wanna talk about what are the type of solutions we wanna address with this product. So today's learning objectives is to identify the criteria for creating a healthy, comfortable, and energy efficient learning environment. I'm gonna turn off my camera for a moment. Then understand the challenges related to poor indoor air quality in classrooms and its impact on health, cognition, and productivity. We also have learned the features and benefits of the SERV1000 as a comprehensive solution for managing indoor air quality, comfort, and energy efficiency. Examine a successful real-world case study in a junior high school classroom. So we want to see how all-in-one solution could be applicable to any school, and then discuss recommended strategies that based on our experience, based on also learning, and how to do cost-effective decarbonization of educational facilities, prioritizing health. So what is the criteria to create a healthy indoor environment? So basically what we are using is all related to concentrations of pollutants. First we wanna understand which ones are the maximum concentrations that we wanna control so the environment is healthy. So basically, if we are outside, we are breathing fresh air, we wanna be inside, there is a lot of pollutants generated inside, we just wanna try to reduce those pollutants to this level. So in general, this the picture that it shows in here is basically the main pollutants that you will find in buildings: carbon dioxide, particulate matter, volatile organic compounds, carbon monoxide, and radon. And if we keep our inside air below these numbers, below these concentrations, we know that it's going to improve health of the occupants. It will reduce sick days by 40% and improve productivity by 10%. So how are we going to know? Basically, well, now technology has been evolving to measure these pollutants accurately and affordably. So now you can find in different, where you buy your electronics, very accurate indoor air quality monitors that they can tell you how is the levels of all these pollutants. Especially now, you can find particulate matter being measured in a good accuracy in the latest monitors that you can purchase through the websites. So we're going to talk a couple about the key indoor air quality, indoor air pollutants. Carbon dioxide, we want to keep the carbon dioxide below 800 parts per million. Usually carbon dioxide comes from respiration and combustion. Outside air, the concentration is about 400 parts per million. That one is the one increasing because we're still adding carbon dioxide to the atmosphere. So it's increasing through the years. High levels, it will give us headaches, dizziness, reduced cognitive function, and also high levels, it's an indication of poor ventilation. And when we understand that there is poor ventilation, there is a probability that you might be able to get or transmit some virus transmissions if you are sick, or if someone is sick, you might be, there is a high probability that you will get sick as well. Volatile organic compounds, these are organic chemicals that easily vaporize in the air We know some of them, they are emitted from paints, solvents, cleaning products, cosmetics, building materials, but I want to emphasize that even if we remove all those volatile organic compounds or those chemicals, humans also emit volatile organic compounds. So high levels, it will get some irritation in the eyes, in the nose. We can get some headaches and long-term respiratory issues. Particulate mass, we also want to control the particulate matter. Basically, what we call a particulate mass or fine particles is basically very tiny solid liquid particles suspended in the air. You see a lot about this PM 2.5. PM 2.5 means that the particles that it's counting or it's measuring particles smaller than 2.5 micrometers in diameter. The smaller the particles, it penetrates deep into your respiratory system. This is a great graph that I found. Basically, yes, everything that is a little bit bigger than 5 micrometers, it will stay through your nose. The nose will be a filter there, but if everything that is smaller, it will go right away into your lungs, and it could actually reach into your blood cells or blood through diffusion. It comes from combustion, vehicle emissions, industrial processes, cooking, construction, wildfires. There are many sources from this. High levels. Some people might experience immediate respiratory issues. Some people will get asthma, very allergies. And high levels and long exposure is now linking to heart disease and lung cancer. So we need to basically, again, take a closer look at this key end air pollutant inside our buildings. Also, there are biological particles. So particles like pollen, mold spores, dust mites are also considered this part of this particulate mass. We will not recognize them when we are measuring, but we know that it's basically part of these fine particles. And bacteria and viruses. Viruses are the smallest, very small, very tiny particle that will be suspended in the air. And viruses can be transmitted, and it could create respiratory issues and probability of infection. So what are the current challenges of school? Now that we know what are the key pollutants that we want to basically follow, what are the current challenges of school classrooms? So now the schools are more in the news. Now they are more into poor ventilation. They're providing news about that there is not enough ventilation. This ventilation is impacting health and cognition. You see news from different news outlets. Also, we went through a pandemic, so there is also kind of like a highlight of, like in schools, there might be some virus transmission if there is poor ventilation. Wildfire smoke is becoming some issue, intermittent issue, depending on the wildfires, what is happening. For example, here I live in Wisconsin. We went through the wildfires from Canada, so it impacted the air quality in our area. And then now we're starting to see some extreme temperatures. And now, just think about that. When you are going to school, you have to basically take a school and protect our kids and our students from all these, all these issues about poor ventilation, contagious viruses, wildfire smoke, and etc. So, well, I think we know. I think you guys know what we want to do. We want to ventilate more. We want to use air filtration. We want to do that. The question is how much we need to do. So that's where we are studying. As Bill Equinox, we did our homework. We tried to understand what is happening or what are the people who did research, universities that did research and understood all this in more detail. So here I'm just going to show a couple of studies, a few studies that basically talk about understanding what is the impact of a bad indoor air quality in children's performance in school. So this is basically the summary of one paper by Professor Ward Kolgig and Bill Basblek and some other universities in South America. They collected data from 2,000 classrooms, elementary, middle, high schools, basically what their conclusion is, increasing ventilation rate in classrooms significantly benefit learning and attendance. And they were able to quantify. So by reducing carbon dioxide from 2,000 to 900, it will improve psychological tests and tasks by 12% in the speed. Reducing carbon dioxide from 4,000 to 1,000, it will increase daily attendance by 2.5%, and so on. There is another study that it was done by just recently this year. It was understanding what is the impact of ventilation and particulate matter in elementary schools in the Midwestern United States. They did a study of 144 classrooms in 31 schools in the Midwest. They also saw similar conclusions: increased ventilation and reduced particle levels in classrooms, reduce the absenteeism in schools, but they quantified as well. Every 2 CFM increase in ventilation was associated with 5 fewer absent days, annual classroom absent days, and increase in fine particles was associated to with more annual classroom absent days. In other words, yeah, there is more particles in the classroom, the people are getting more sick, then there will be more sick days, but then now it's a little more these studies are quantifying the impact of indoor air quality. Now, there are also, I'm bringing it to your attention, also some studies that they have been done in offices, for example. Offices, it means there is people gathering together in one room or in one big room. So we want to understand that as well and use that to basically use the learnings from offices for schools as well. So this one is a study that they took 40 buildings comparing 25 CFM, comparing 2 rates of ventilation, 25 versus 50. Just to understand which one is better. Of course, we know that which one is better, but they quantify the results. So there was a 35% increase in short-term sick leave with the lowest of the ventilation rate. So now they're starting to give us kind of like some numbers that we should be targeting with our ventilation rates regarding, for example, 50 CFM per person here. And of course, like if employees get sick, then there is gonna be some losses on money as well, on the income from the company and so on. So there is another study where they take a closer look at carbon dioxide, ventilation, volatile organic compounds in workers. They also saw similar effect. They quantify the effects as well. For example, this one is controlling indoor volatile organic compounds, increase the cognitive scores, basically your thinking, by 61%. That was a major change by just taking a closer look at volatile organic compounds and controlling them under the healthy levels. And then doubling ventilation, increased cognitive scores further by 100%. So those are the type of studies that is giving us kind of like all the requirements that we want to set when we are starting to design our products. And the last one is the impact of bad indoor air. This was more of an economic study, just understanding how much, if you're increasing ventilation, you want to increase ventilation, how much it will cost. So they estimated about a $40 per person per year if you increase the ventilations from minimum standards. Minimum standards are typically 20 CFM per person. All the studies are pointing towards 40 CFM per person to create this healthy environment. So that increase from 20 to 40 CFM is only $40 per person per year. Without energy recovery, if you add an energy recovery ventilation, it will significantly reduce energy costs. But also not only it will cost, but increased ventilation, it will improve the worker performance by 8%, equivalent to $6,500 per person per year. So there is a lot of benefits, not only on the health, but also productivity of the people inside the building. I'm gonna use this a little bit just to address viruses. Usually today, viral diseases are treated by medicine. So you get sick, you go, or you get the flu shot and so on and etc. we went through a period where there was a disease or was a virus that didn't have a vaccine. So we went through a period of basically isolation. But right now, I think we're starting to see that ventilation and filtration were not typically preventing measures, and now they are promoting that. So we're seeing more promotion, especially from the ASHRAE. ASHRAE stands for American Society of Heating, Refrigeration, and Air Conditioning Engineers, to start putting better filters in your air conditioning system, and also increase the fresh air into your building. One recent study, actually, there was a connection where it provided a real world evidence that they saw a decrease on a virus, or in this case it was COVID-19, with increasing ventilation. So there was a direct, a more real world results, where it was showing that yes, also increasing ventilation will reduce the virus, the potential, the probability of you getting sick. It will be reduced. So now there are some other things that we say, okay, well, let's try to measure the indoor air quality in schools. This is a new paper that measuring, well, here what I'm trying to say is that the measuring indoor air quality is not enough. We really want to measure, but also control the concentrations inside or classrooms in this case. This was a critical paper where basically they focused on the Boston public schools. It was a missed opportunity. They invested thousands of dollars in indoor air quality monitors. They purchased portable air cleaners with HEPA filters, but they forgot to focus on the ventilation. So there was no significant improvement in their indoor air quality because we are producing not only particulates, but also carbon dioxide and other chemicals inside the room. So, but the major is basically the proper ventilation is crucial for reducing virus transmission risk and improving academic performance. So basically the current state of schools is the news are reporting highlights that basically schools have lack of adequate ventilation. It doesn't have proper HVAC systems. Schools now we're starting to get we need to be concerned more with extreme temperatures and wildfire smoke events because it might occur more frequently. But there is a lot of studies that they have focused on those issues, and then basically is more ventilation improves the student. Is now very well documented that more ventilation improves the student health, learning attendance. Lowering fine particle levels also boosts health and reduces absences, and doubling ventilation could cost under $40 per person per year with no energy recovery. And the recent research confirms that better ventilation can help reduce airborne viruses spread in classrooms as well. So basically what I'm trying to prepare here is basically what are the type of recommendations. So the recommendations, as this is basically the background of the explanation of all these healthy indoor air quality guidelines. We want to keep all these pollutants under control below these levels, and then we will achieve a really healthy indoor environment. So how we do that? So mechanisms to reduce pollutants. So shall we put filters? Shall we do ventilation? Shall we put ultraviolet germicidal irradiation? I would say that the most effective system is the one that uses them all. Definitely we have to have ventilation. Filtration helps to reduce the pollutant levels, the particle levels, and microbe deactivation. It will make filtration more effective for those biological agents. So that's how we start building this indoor air quality management system. So for recommendations on how to build a really truly healthy building, first, ventilation. Based on all the studies that I just showed you, the ventilation has to be higher than 40 CFM per person. That's equivalent to reaching healthy level of 800 ppm CO2. So in other words, it's not about the target 40 CFM. That is 40 CFM is the typical ventilation rate that you might need in order to get a healthy level of 800 parts per million of carbon dioxide. Air filtration, this is all based on ASHRAE studies and the studies that I show you. MERV 13 or higher. MERV is a designation of the filter. Basically, is the efficiency of the filter. 13 is basically one of the designations. So we can use that for air recirculation, for fresh air coming in. And as I mentioned, if you want to reduce all the biological particles like viruses, bacteria, and so on, then you can use ultraviolet germicidal irradiation that it will make more effective the filter, trying to remove those biological agents. Now that we have kind of like the recommendations on how to do it, we want to do it smartly. When I say smart ventilation, is basically make it efficiently, do it efficiently. And what is efficiently? It's basically if we monitor the pollutants, we can ventilate when needed because we know that the pollutants are high. We need to bring fresh air in, or if there is some fine particles that they are high, we can maybe use the filter more often. We can use variable fan speed to supply what is needed. So sometimes it's not needed to have those 40 CFM per person every time. Sometimes it's maybe there are only a few people in the room, so we just provide. Basically we can just provide enough to reduce the pollutants. And then ballast ventilation, usually energy recovery. Conditioning the fresh air with exhaust air is a good measure to reduce the energy consumption. And also recirculation mode. Sometimes we don't need to ventilate all the time. Sometimes just by recirculating, we can actually even some spaces that they are high concentration to low concentrations to make it more even by using more the recirculation mode. So now that I gave you a lot of the background on what are the targets of an all-in-one solution, I would like to explain basically all the design that we put together inside Build Equinox to create this all-in-one solution. So we call it the CER 1000. 1000 is basically 1000 of CFM, basically cubic feet per minute, for a space like a classroom. So what is this all-in-one unit? Basically, we created this solution based on all the issues that I just laid out. We want a solution that is basically, we want to address everything, basically healthy, keep the students healthy, keep them comfortable and in their indoor environment, basically in the classroom. So the first thing that it has to have is basically an efficient cold climate heat pump. This is a one system for space cooling and space heating. You guys are maybe getting very familiar with heat pumps, especially now that we are moving towards more into the electrification, more into reducing carbon emissions into the buildings. Heat pump is a great solution for that. So definitely it's going to reduce the carbon emissions. Definitely it's going to reduce the energy use of your building by moving towards heat pump. But then also we want to integrate that heat pump with a smart indoor air quality management system. As I mentioned, a smart system means that we want to monitor the pollutants all the time, especially carbon dioxide, volatile organics, particulate matter, inside, outside. So when we want to reduce the pollutant gases, we want to reduce the fine particles based on the logic that this system will have, and then also deactivate germs. We want to do all of it: reduce pollutant gases, reduce fine particles, and then deactivate these biological agents. That's what we want to do. So then what we decided. So how are we gonna do all that in one box? So this is basically a small diagram of a classroom where basically we want to have some system that is going to bring some air, maybe dirty air, and then we want to clean it up. First of all, we want to add the comfort level. The comfort level is the cold climate heat pump. The cold climate heat pump is going to exchange, in this case, it's going to exchange with the air. So it's going to be an air source heat pump. We want to make it efficient for cold climates. So we choose a cold climate heat pump. This one is gonna help condition the air that it's coming to basically that is gonna go through to the classroom. To make it an air cleaning solution, we wanna use MERV 13 filters. So we wanna filter that air to remove those particles that they might be generated inside. And then to be more effective for biological agents, we add in this ultraviolet germicidal irradiation, basically a UV light that we are just adding as well. This is more for the biological agents to deactivate viruses and so on, that it would be very effective if we combine it with a MERV 13 filter. In ventilation mode, sometimes filters, they only remove particles. We also want to remove gases. So that's where we put in our unit an energy recovery ventilator. Basically, we just want to bring some of that dirty air that is inside, just exhaust it outside and bring fresh air coming in from the outside and put it in. That will help us dilute all these pollutants inside the classroom. We want to make sure that the air that it's coming in is filtered. Sometimes the air outside is dirty, so we want to filter it. There's sometimes there is construction, sometimes there is a lot of vehicles passing by, that there will be some fine particles outside. So we want to filter that before it comes in our classroom. So that's how we put a MERV 13 just before. And also, of course, smart controls. Basically, we have a variable speed fan, variable speed compressor. We have a damper system that it helps us to see if we want to recirculate the air or when to bring fresh air in. Sometimes we don't need it. Sometimes the room is empty, so we don't need to ventilate all the time. But sometimes now there is a point where all the kids are there, and then we need to bring fresh air. That's where we open the dampers and then bring that fresh air in. So, and then they make it more smart is by putting in basically sensors indoor. We measure temperature, relative humidity, carbon dioxide, volatile organic compounds, particulate matter, particulate count. Basically, this is all for fine particles, just to measure what's happening in here. All this is gonna provide the signal to all the controls to tell us what to do to clean up the air inside. And also we are measuring outside. Sometimes the outside air, it might be polluted. So we wanna make sure that we are bringing really good fresh air and clean fresh air to the inside. So that's basically the diagram of what is inside this CER 1000, this all-in-one unit. So it has a heat pump and an indoor air quality management system. So now to talk a little more in detail, it's more about what are the type of specifications. So this is more of a 3-ton BTU heating and cooling capacity. What it means is that, yeah, this is basically designed for classrooms. Classrooms typically are about 25, 30 people, 30 kids inside the classroom plus the teacher. So this is designed to keep comfortable kids for the extreme temperatures. So this will work from -15 Fahrenheit to 115 Fahrenheit outside temperature operation. It's a cold climate heat pump. It means is that the capacity is not detrimental with the temperature outside. So at -15 degrees Fahrenheit, that's very, very low. The steel will have about a 70% of the rated capacity that it was designed for. As I mentioned, ventilation for us is a high priority. There is basically, we know that ventilation is gonna make the classroom healthy. So we want to get up to 1,000 CFM. 1,000 is basically 25 kids, 40 CFM per person. That's what it gets, the 1,000 CFM. But then we use energy recovery, basically energy recovery course, that it will give us about 80% sensible, 60% latent energy recovery in this course. Variable speed fan, as I mentioned, we sometimes we don't need 40 CFM per person all the time, so we just have our logic to increase the speed when when the carbon dioxide goes up. And as I mentioned, this is all demand control ventilation. We're monitoring not only carbon dioxide, but also volatile organic compounds and particulate matter level. Sorry, particulate fine particles inside the classroom. So we have indoor and outdoor sensors. So it will help us to provide with the HVAC controls, 100% ventilation when it's needed, or just 100% recirculation to keep the air conditioned, but also filter and so on. And the air purification capabilities, the standard MER13 filters for both for the inside, just for the return air, and also for the fresh air that is coming in. And we also have some LED lamps, ultraviolet LED lamps that is gonna have help us to basically deactivate all these biological viruses, bacteria, and so on. Kill them. Just quick, how to say, features that we are very excited to bring in here in this CER 1000. It's a built-in Wi-Fi. You basically will have a free app. This is a screenshot of the free app in your phone. It will allow users remotely monitor and adjust settings, provide real-time data and alerts, enhance user convenience, simplify management. We'll have flexible scheduling options. Sometimes, for example, we can set up the weekends to basically turn it off. We don't need that, or maybe there are some specific days of the year that we need to have more cooling, more heating, or you can set up your CO2 set point, VOC set point. We can create extra ventilation. Some places, maybe somebody brought a chemical kit to play, so we need that extra ventilation in some cases, et cetera, et cetera. Use an ocean, wireless communication, wireless data transmission for building automation, and so we can integrate with other sensors and so on. And over the air capabilities, we can actually also introduce new functionalities and improvements to this CER 1000. So this is the description of the all-in-one unit. So one of the major things that we recognize is basically the facility manager. The facility manager wants to also understand what's happening in each of the rooms. So you should be able to the building manager or principal or somebody that wants to care about the school has a dashboard that can take a closer look at each school. What are the levels of carbon dioxide? What are the levels of volatile organic compounds, energy efficiency, et cetera, et cetera, et cetera. Not only that, it can do some diagnostics. It can provide some scheduling for replacement of filters, ultraviolet lamps, et cetera. And not only that, so if it works for one building, just a few classrooms, it could be also applicable for basically a full school district. One person can take a closer look and understand what is the indoor, the current state of the indoor air quality in each schools with this, by bringing ventilation and making it. So it has a really great capability just for one person to understand the state of the indoor air in schools. So now that I described what was the big problem, the problem right now is, yes, poor ventilation and some extreme weather issues that we might need to as well to solve, but especially it's poor ventilation affecting the students in the classrooms. So now we've created this product, this new all-in-one solution that is not only just provide comfort conditioning just for heating, cooling, but also a smart ventilation, smart filtering system that it helps you really control the pollutants inside your classroom. So now we build it. We want to understand the effect of this product in the real world. So we have a case study, a junior high school classroom where we use one of the products there. So I want to show this is because I don't know, I forgot to ask, who are you guys joining us from? But I live, for example, I live in Milwaukee. That's a pretty cold temperature. We are pretty high in the northern side of United States. The school that we put this system, it's in Illinois. It's basically near the border between Illinois and Indiana. The design conditions are typically pretty, I mean, it's a pretty cold, still we get there pretty cold winters. So the design condition about 0 Fahrenheit of temperature for design conditions, but also gets very high and humid, very high temperature and high temperature and humid. So it actually could be extreme, basically going from very cold to very hot and humid. So those are the type of conditions that you could see in this type of school. So just to give a more description of this, this is a rural school, about 200 students, 25,000 square foot. And the current state of, like today, except one room where we installed the CER 1000, basically they have no ventilation. There is no rooftop unit. There is nothing. There is just no ventilation. There is a radiator, basically radiators in each of the room, basically a baseboard heater. Here is a picture of that, basically a baseboard heater that it provides the heating for the students, and a window air conditioning that it shows in here as well. Just an air conditioning for cooling of the 25 kids inside this classroom. The exterior wall, I think that this was added. It was an add-on. They created an insulated wall with reduced windows, just as an add-on for the school, trying to reduce the energy loss. But in general, that's basically the system that they have. That's the current state of the classroom. So what's happening inside the classroom? So we were able to measure indoor air quality before we install the CER 1000 into this. So I want to just provide this graph just to explain. Here you're gonna see the pollutant that I'm measuring in here. Here is basically the date of measurement, and then you will see kind of like a pattern. The pattern is basically this was Thursday. It goes up, it goes down, it goes up, it goes down. There is the weekend. This was Labor Day, and then Tuesday and Wednesday basically is following that pattern. So this will show here the location of the indoor air quality monitors. In this case, I'm just showing the data of one classroom. The lines here, the black lines are midnight. Midday means that is basically in the middle of this, between the two black lines. And then this is like a 6-hour period is with these small grids in here. So this is kind of like showing that. And here is basically, this is like data from a school classroom, about 750 square foot, 26 people, 25 kids, and one teacher. And you will see right away at 8 o'clock in the morning, the CO2 spikes right away from basically 400. Basically, this is the level of the outside, just right away into 2,400 parts per million. And then when the kids leave, just boom, it just goes down through the night and it starts over. And you see a very, very distinct pattern when the kids are inside, when the kids are not inside. So what is our target range? We want to have all these peaks just below this line. So as I mentioned, for carbon dioxide specifically, it's about, we wanna keep this under 800 ppm parts per million. So we want to keep all, basically the carbon dioxide levels below this healthy range. So that's basically our target. So now I just want to give a little more data. So we didn't measure only one classroom. We measured about 3 classrooms in the same school. The condition space is about as I mentioned, 750. I would say this is a leaky building. As I mentioned, there is no ventilation. There is an energy assessment that they did. They take about 200 kilo BTUs per square foot per year. This is basically the energy use intensity. So they're using energy, so they measure the energy. So when I compare, here are the carbon dioxide and volatile organic compounds. I want to spend a couple of minutes in here is because of the pattern. First, the three classrooms are basically behaving exactly the same. You see that when the kids are inside, you know when the kids leaving, and every day. As I mentioned, there was 3 days where the carbon dioxide was low, basically healthy, but it was because no one is there. No one was there. Then it goes again. The kids show up, it will go up, and so on and so on. Similarly, volatile organic compounds. So here there is no cooking, there is nothing, there is no nothing, and there are still volatile organic compounds being created in this room. So that means that this is coming from the kids as well. So also the volatile organic compounds go into high. We want to keep these volatile organic compounds below, the VOCs below 125 parts per billion. And you see the same pattern. So you see that this is all people related. There is no people in here. The volatile organic compounds are low, then it comes back. There is some interesting patterns in here. If you notice, it looks like they are cleaning, that people maybe at the end of the night, they are putting some cleaning products. So this is different than the pattern that is showing in here. So that means that it's not people, but there are some people that are using cleaning products and so on. So that's where we want to basically address. We want to lower those, all these chemicals, those gases as well. So we install one unit in one of the classrooms. So right now we are working on 12 classrooms. We want to basically this wing of the school. We want to we have a project to fill this, or basically to install the CER 1000 units in all of them. We already completed one. The process that we do is basically a room by room rolling installation. We install this, and it's flexible. We started one in the summer, and then now we are preparing to install the other ones at the end of the year to do that one. But is this one of the things that I want to highlight is this is a room by room rolling installation we want to do. So what was the results from a pollutant point of view? So I'm showing here carbon dioxide. So this is the case with no ventilation. So as I mentioned, it reaches higher than 2,400 parts per million for carbon dioxide. Right away when we turn on the CER 1000, there was right away a 1,500 parts per million difference. So we really reduced the pollutant levels for this particular classroom. So now the question for you guys probably says, so why we are not below the 800 parts per million that we are targeting in here? It was right now is difficult because there is some cross-contamination. So we were understanding what was happening in there. And usually these doors are usually open to the hallway. And then we went with some indoor air quality monitors, and we measured the hallway, and the hallway was about the 2,000 and higher. So that cross-contamination of carbon dioxide from other rooms, other classrooms, was creating this cross-contamination issue. So when we complete the project, we want to measure again, but we are very confident that those levels of carbon dioxide are gonna be below 800 particles per million. So if I show what was before and what was after, definitely it was a major change in the contaminants, in the pollutants concentrations. We were able to reduce carbon dioxide by 1,500 parts per million. And you see these are basically the similar dates. This was in 2022. This was in 2023. So it's a very remarkable, very successful story about bringing that 1,500 reduction on carbon dioxide is a major health benefit for the students in this particular classroom. So this is a screenshot of basically what you could see in the website, or basically in the dashboard of this system of the CER 1000. So here it's showing outside particulate matter and inside particulate matter. Outside was pretty clean. Basically, there were some spikes of particulate matter in some times, but in general, the inside was always below or recommended values of 10 micrograms per cubic meter. I mean, it would be interesting to see this is when there is a effect of wildfires in this particular region. So I know that they had that during the summer, but we didn't have the equipment to measure ready for that time. Low energy consumption as well. So the green, it shows when the ventilation is activated. So definitely we wanna basically use the ventilation when the kids are inside in the classroom. So that is showing, the green is that the ventilation is running, the fans are running. But now there is a point where, okay, now the levels are below 800, so you don't need to ventilate anymore until the next day. And here it shows that the ventilation of the unit was basically turned off the whole weekend until the following Monday that the kids show up again. Regarding noise, we were able to also measure the classroom with the noise of the window AC. It was okay, I would say 63 is still quiet, but I would say this is more related to a normal conversation. Then with the installation of the CER 1000, we were able to reduce by 10 decibels. 10 decibels is a major change where now it is even quieter than before. So also we are using a very quiet fan to, even though we want to increase the ventilation rates for a healthy environment. From, let's see, what is the time right now? 10, I'm gonna see if I can go through, but I'm almost there in the slides. But basically, we also want to reduce carbon emissions. So, but I think what the message today is we really need to prioritize on the health of the students. Increase ventilation, use air filtration, and also to reduce the viruses complemented with UV lights. So this is a table. Now let's switch a little bit the discussion on reducing energy use, reduce carbon emissions. So we also did our homework on kind of like what is the electricity use. It was about 305 megawatt hours. This is per year. This is the yearly rate. Gas use is about 43,000 terms. They are paying about 50,000 per year on bills, energy bills for this school. By dividing it by the square footage of the school, it will give us about 200 kBTU per square foot. Basically, this is energy per square foot, and carbon emissions about 360 tons of carbon dioxide per year, equivalent carbon dioxide. So where are we? So if we do a benchmarking, the benchmarking we typically use Portfolio Manager for commercial buildings. We have to be, this is the median. The median is about 50. So if you compare 200, basically this school is spending a lot of energy, more than the median of a typical US school in the country. So we did an estimation. What happened if we get all the building, all the classrooms to get this all-in-one CER 1000 upgrade? So the first thing is the site EU, the site energy use intensity was reduced by 70%. This was thanks to the heat pump that it reduces the energy. You see the switch here. The electricity use will increase because of the heat pump. We are now using more electricity to run the heat pump. The gas use definitely reduced significantly. This is more related to water heating. Right now, we're just not using solar yet, but the carbon emissions also was reduced by 40%, energy cost was reduced by 7% by just putting these systems. This is an estimation, putting these systems into the classroom. Now what happened? Now we didn't get into 60 below 50, but it's because we only did the estimation of changing to heat pumps. But usually we have to combine it with change it to LED lighting, maybe do more air sealing, more insulation and so on to the building to maybe reduce this further. But then if I add a solar PV system, this one we just take into consideration the area that is available in the roof of the building. It will give us about a 200 kilowatt system that we can add into the roof. So if we did that calculation, now on my carbon emissions, I will use the same energy because the energy will be exactly the same, but now my carbon emissions will be reduced by 70% by just putting that solar PV system in the roof. And also the energy cost, because now I'm using more energy from on-site generation, my energy was reduced by, energy cost reduced by 45%. So those are estimated values, but that's basically something that we are gonna guide the school to follow with this type of recommendations. So I'm gonna finish basically with recommended strategies for cost-effective building decarbonization. So the first thing that we wanna do is reduce energy use. Reduce energy use also reduce the heating loads that we need for the building. We don't need to use a lot of energy to heat up or cool down the spaces. Usually it's weatherization, insulation, and air sealing. Some people will, depending on the application, some people might need to do windows upgrades, and then full conversion of LED lighting. LED lighting is more efficient than the incandescent lighting, so those are the type of things that we want to do just right away. But one of the things that I want to make sure that you guys get out of this webinar is that we really need to, at the same time, improve health. So in other words, we also need to parallelly or doing it together with weatherization is improving health by putting an indoor air quality management system, hopefully a ventilation system with an ERV that help us remove the pollutants inside. Now, after we finish those, then we can electrify the building by putting a heat pump for space heating and water heating, and then, sorry. Now, just before I go with the next step, I just want to talk about air sealing in buildings. So we hear a lot, yeah, definitely air sealing buildings will reduce air infiltration, it will minimize energy loss, offers a barrier against external pollutants. Sometimes there is a lot of outside pollutants like construction, all that. So sealing it, it will help out. There is pollen, there is wildfire smoke, there is moisture that we can actually control by sealing it. But also, we need to understand that by sealing the air, the building by itself is gonna also contain the indoor generated pollutants. So they're preventing the air pollutants to get out. So that's when I say about air sealing buildings, it has to be integrated with an indoor air quality management strategy to remove those pollutants, to keep that flow, so you can control the air coming in and coming out. But it's essential that you bring fresh air into your building and a fresh filter air. So now that with this strategy, basically now, yes, now that we have all the electric equipment, we have the ERVs, we have the filtering system, we have the heat pump, it's all electric. Now let's supply that energy, most of the energy, hopefully 100% of the energy with a renewable source like on-site solar PV. So now, if we are using the CER 1000, the best part about it is that this is an all-in-one system. So not only does the indoor air quality management, but also it has the heat pump capabilities. So it basically now reduces the number of steps into one, and that's basically what people are wanted to see, is have these all-in-one systems to basically reduce the installation and the renovation activities. So I want to finish is by with comments about centralized and decentralized systems. So a typical school building will have a central boiler. So the boiler will basically provide through a set of pipes, and system will have hot water going through these radiators, and the radiators will heat the classroom. Usually the cooling is a separate system. It could be windows air conditioners, as the case that I show you, but it also could use some chillers and use the same hydronic system, or some rooftop units where it has this air duct work that it will help to send basically cool air through the classrooms. So one thing when you are into the decarbonization or this renovation phase is that we just learned that a major % of schools in the US have poor ventilation. So just by replacing the boiler, and usually the boiler replacement is typically two. It will be a ground source heat pump, also known as a heat pump, a geothermal. I'm talking about centralized systems, or a variable refrigerant flow VRF system with forced air. Just the boiler replacement alone doesn't address indoor air quality issues in schools. I agree that it removes combustion from the schools, but it doesn't address the indoor air quality because there is pollutant generated inside the classrooms. So that's the pollutant that we need to reduce. So to enhance this centralized system, the system that use ground source heat pumps, variable refrigerant flow, and so on, we need to, the recommendation is to add a dedicated outdoor air system. It will be required, and that's what we will recommend, is to put also ventilation system together with a ground source heat pump, for example. So when we talk about this centralized system, it's gonna be a major infrastructure modification required, because when we are using a heat pump option, when you are using a geothermal heat pump, you have to create this ground coil to exchange the heat between the ground and the building. If you are using a VRF system, you have to basically create this refrigerant network inside the building to basically distribute the refrigerant in your building. But then we are recommending adding this dedicated outdoor air system. So you also might have to install a central air ductwork if it's not existing. So when doing this analysis, cost analysis, we're estimating this cost of this centralized system to be between $50 and $60 per square foot. What we are basically saying is let's take a closer look at this decentralized approach using where we want to remove the boiler, decommission the existing hydronic system, and then install this all-in-one SER 1000 unit for each classroom. So it's basically to have this unit in each classroom. This is another approach that we call it a decentralized approach. This is more of a room by room, rolling installation, flexible scheduling, minimal time disruption. And what we are seeing is the estimated cost based on our analysis, about 30 to 40 square foot. So definitely going room by room is going to be faster in installation, and also less cost on the component and so on needed. Let's see. Okay, I got 1 out of minute, but any questions that you might have? Let's take a closer look at the questions.